Without further ado, let's hear from our students. And to get us started, I'd like to turn things over to the president of Gopher Motorsports, Wyatt McCarthy. Wyatt, go ahead and take it away.
Hi, thank you all for coming here. We're really excited to show you guys some of the work we do and what we do here at the U of M. A little bit about myself. As Joel said, I'm Wyatt McCarthy. I am a senior in mechanical engineering. I should probably share the slides. And so I joined my freshman year. So this is my 4th year on the team. And just for a little bit of background on what is Formula SAE, it's an international student engineering competition to design and build open wheel race cars. And the design requirements are fairly open-ended. Of course, there's plenty of safety and size requirements. But the main rule is every year you have to completely rebuild the chassis to be able to compete at a competition. For a little bit of info on the competition, it's kind of broken down into 2 sections. You have your dynamic events and your static events. The dynamic events are mostly are the events where the car is actually moving and you're testing the vehicle. So you have acceleration, which is just to see who can accelerate the fastest. Skid pad, you drive in a circle to test the max lateral Gs. Autocross is a 1-lap race, and then endurance and efficiency are part of the same event. It's a 22-kilometer race to see who can get the fastest time. And how little gas you use or electric battery is part of the scoring competition. And then there's also the static events, which are kind of the knowledge-based things. So we have the design section, which we have to prove to professional engineers how our designs are quality and how we can mathematically prove that this will be a good car. There's a design presentation where we take a business case scenario and we have to present how our team would handle that. And there's a cost event, which kind of benefits teams who can build cheaper cars. So there are 2 vehicle classes right now for Formula SAE. There's the internal combustion class and the electric class. Currently, we're competing in both of them. This will be our 2nd year building both cars. The IC car, of course, has been around for about 25 years now. Or the electric car, like I said, this is our 2nd year. Over the years, we've had some really successful finishes, including in 2019, when we got 9th place at the Michigan competition out of about 120 different teams. And so our team is made up of 5 primary officers and 7 sub-team leads. I myself am the president, and then each car has a chief engineer who kind of makes the goals and objectives for that specific vehicle. And then we have 2 project managers, one focused on general timelines, and then one who's focused on manufacturing. And then we have the 7 sub-teams listed on the right. And so about the kind of composition of the team, there's really no major or age requirements to join the team. We don't have any applications or joining requirements, except for people who want to learn how to build a car and learn more about engineering or whatever they're working on. And obviously, we mostly cater to engineers, especially mechanical, aerospace, and computer science. But we also have people from all across the U, including many Carlson members, as well as even a pre-med major. So anyone can join and be a part of the team. And I'll hand it off to Will Manderfeld. He's our IC chief engineer to talk about the IC car.
Hey everyone, I'm Will Manderfeld. I'm a senior in mechanical engineering, and it is my 4th year on the team. So I'll be introducing the IC vehicle, which stands for internal combustion. It is powered by a 600cc 4-cylinder from a Yamaha R6 motorcycle, the engine we've ran for a long time now. It's the 2nd year of doing a carbon fiber monocoque chassis. The aggressive body styling is part of our high downforce aerodynamics package, which Alex Odi will talk about in a bit. And we also have a custom onboard data acquisition system that Calvin Molitor will introduce later on. Pictured on the left is our last year's vehicle, the Gopher 22C, after our May competition at the Michigan International Speedway. This was the first competition spec vehicle we had built post-COVID. So it's kind of a drastic redesign over our previous iterations of car. Next slide. So Gopher 23C, pictured on the left, is the vehicle we're currently designing and building, and is the 2nd iteration of this new vehicle platform. This new vehicle is going to be built around a strong design philosophy shown on the trifecta wheel on the right, meaning it will be a lightweight, robust, and fundamental vehicle. Overall, we're targeting a 5th place finish at the competition this year. In order to achieve this, just a couple overall vehicle goals. We're aiming for a vehicle less than 440 pounds without a driver. Our downforce goal for our aerodynamics package is 270 pounds at 50 miles an hour. So when you factor in the weight of a driver, that's almost half the weight of the vehicle. And that's not even at our top speed. And then also have the engine produce at least 75 horsepower. With that, I'll introduce Sophia Clark, talk about the electric vehicle.
Hi, my name is Sophia Clark, and I am the chief engineer of the electric vehicle team. So we are a second-year team building an electric vehicle. What's pictured on the screen is what we brought to competition last year, where we placed 16th place out of 80 teams. So really good for a first-year team. This year, we're targeting a top 10 finish, and we're working around a new design philosophy. So the EV and the IC differ on a couple of things. The EV is really a new innovation space. There's a lot of challenges that we haven't seen before as a team, and it's not like we're iterating off of previous designs. We're also looking at a more stringent roadbook. Our Q emitter is 350 volts, so it's a high voltage system. So we have to be really, really safe around that and make sure that we're building safe components. So we're trying to build up our new member space and also design documentation, as well as tinkering, making things work, and then also having simple, reliable designs that will work for future iterations so we can build up a stronger, better car for next year. So you can go next slide. And then I'm handing it off to Alex Odie, who's going to talk about our aerodynamics sub-team.
Alex, we can't hear you.
What about now?
Yep, I can hear you now. Thanks.
Okay, sorry about that. All right, so I'll start again. My name is Alex Odie. I'm a junior in aerospace engineering. This is my 3rd year on the team, and I'm the aerodynamics lead. So on the aerodynamics sub-team, we're responsible for the design, testing, and manufacture of 2 aerodynamics packages, one for our electric vehicle and one for our internal combustion vehicle. We run an aerodynamics package in order to increase the load and therefore grip on the tires without significant weight addition. Next slide. So the first part of any aerodynamics development is the design and simulation. We design a high downforce aerodynamics package using SolidWorks CAD, as well as a parameterized wing generator that the team developed using MATLAB, shown in the bottom left. This is a software that we developed to help us increase the turnaround time on our designs, and also helps fine-tune airfoil placement. We also use a custom lap sim to help validate design decisions, also in MATLAB, shown in the bottom left, or the bottom. This graph shows a study that we ran for flat position of the front wing and the rear wing as a function of radiator mass flow to justify flat position while maintaining our cooling performance. This helps us get optimal goals for downforce, drag, mass flow, etc. The most important tool for design and simulation of the aerodynamics package is CFD, or computational fluid dynamics. This allows us to test designs before we build them, using industry software to allow us to figure out what's going to happen before we actually do it. We validate our current geometry with this, and we can figure out areas of improvement to further fine-tune and perfect our package. Some examples of this are shown on the right. The top right photo is a study that we ran a few days ago, looking at the vorticity of the fluid within our side pod structure, looking to figure out how we can optimize vortex creation to maximize downforce. The bottom right is a pressure plot on our rear wing. With this study, we were looking at how the roll hoop and driver, engine intake, etc., affect the pressure distribution along the wing and therefore the performance, as well as analyzing wingtip vortices shown with the flow trajectories on the right end plate. These are just a few of the examples we can do with CFD. Next slide. So the most important part after the design and manufacture of our aerodynamics is the manufacturing and analysis portion. We use a full carbon fiber design just due to its lightweight construction, as well as being strong in tension. I actually didn't mention this on the last slide, but we use a custom wing internal system, which puts the airfoil skins actually in pure tension to resolve the forces. So these photos on the right in the top center is an infusion layup of our diffuser last year. And the bottom right is a wet layup with a vacuum bag. These are two of the most basic manufacturing techniques that we use. We use these for most of our parts in the car. We do our layups and our composites manufacturing fully in-house on 3D printed airfoil molds. Examples shown in the top right due to us with help from a sponsor in the local area. For the analysis side of things, this is arguably the most important part because it doesn't matter how well you design it, it actually has to perform. We use a variety of qualitative and quantitative measures. For a qualitative measure shown in the bottom middle, an example of this is tough testing. We attach pieces of yarn to the lifting side of our airfoils to look for turbulence, recirculation, validate our CFD models to see if we're seeing what we expect. And for our quantitative data analysis, we use Motec i2, which our electrical lead Calvin Molitor will talk more about, to analyze, say, shock position at various speeds to help quantify our downforce and our aerodynamic forces. So with that, I will hand it off to Sylvia Burka, our engine lead.
Sylvia can't make it today, so I will be filling in for her. The engine sub-team handles the IC powertrain and the electric vehicle drivetrain. Next slide, please. So engine team is responsible for maintaining a working engine and all the components that come together to make it run. The team uses an inline-4 600cc Yamaha R6 motorcycle engine and has been using that same engine for the past few years. Some of the designs that the engine team handles is designing and manufacturing the intake and exhaust manifolds, lubrication systems for the engine, and the drivetrain for both vehicles. Over the years, they've made alterations to some engine internals, including a lightened crankshaft, thinner flywheel, and custom camshafts that reduce the valve lift and overlap due to the air restriction requirement in the competition. Next slide, please. One of the biggest tools the engine team utilizes in the design and validation is a water brake dynamometer, which you can see as the yellow circular machine on the left. This dyno is essentially a car without wheels. It allows the students to test and validate the designs before the car has been fully completed or before we can really start driving again due to the never-ending Minnesota winters. They can install their designs on the engine we run on the dyno and do a lot of tuning and testing to validate the actual performance of the engine with these changes. There's also, the team also uses software to simulate internal combustion to design their intake and exhaust manifolds and really optimize the performance. In addition, students do a lot of hands-on work rebuilding engines and changing out engine internals. Next slide, please. I'll also be covering frame suspension as the lead. Emma Vosley could not be here. These images show some of the cool areas that the frame suspension sub-team is involved with and kind of the envelope of that system's design. Next slide, please. So I can start with the frame. The frame is the basis of the entire vehicle and comprises what everything else attaches to. It is very critical that it is both stiff and also very lightweight. Our electric vehicle uses a steel space frame comprised of an array of steel tubes in space. As you can see in the bottom right, that is the manufacturing progress of the electric vehicle space frame. The internal combustion vehicle uses what we call a hybrid chassis. The front section of the chassis, kind of where the driver sits, is a carbon fiber monocoque. If you're not familiar with what a monocoque is, it's basically just a shell. And then the rear section, where like the engine sits is a steel space frame, much like the EV car. We design and manufacture both of these frames entirely in-house. So for the electric vehicle frame, we do all of the TIG welding, tube fitting, and fixturing on the table in mechanical engineering building. The carbon fiber monocoque, we make the tooling for and do the layups entirely in-house as well. Should be mentioned that we also do material testing on the carbon fiber to validate its stiffness and strength for both safety reasons and design reasons. Next slide, please. The suspension system refers to all the components between the tires and the frame. Every component is very rigorously analyzed for both mass savings and strength analysis and stiffness analysis. It is very critical that these components are as light as possible, while also remaining stiff and strong, which makes for some very interesting looking designs that we also still have to be able to make ourselves. We do make most of these components in-house. The picture on the bottom right shows the post machining of one of our uprights. This was done on the CNC in the Polaris student machine shop. The upper two pictures are using ANSYS, doing some finite element analysis on these components to ensure their stiffness meets our standards. And then the bottom two pictures on the left show our suspension, our carbon fiber control arms, and our front suspension packaging on the electric vehicle. Next slide, please. Final thing frame suspension is responsible for is the vehicle dynamics and tuning aspect of the vehicle, determining how the vehicle will actually perform in real life, handling wise. We do a lot of mathematical modeling in order to predict how the vehicle will perform before we build it. And we also test what changes we can make to the vehicle to see what would have the greatest impact on performance. After the vehicle is built, we do extensive testing and data gathering in order to validate these models, doing simple tests in real life while driving, and using our data acquisition system to compare to our model outputs. We design a lot of adjustability into the suspension system as well, so it can be dialed in during our testing process to maximize our vehicle's performance. The upper right picture is actually a tire model. So we mathematically model our tire using test data from an external sponsor. The bottom right is a kinematic model. It's how we test the suspension through its full range of motion and see like how it moves before we actually build the car. And then the bottom two pictures is just an example of an onboard camera while driving and some of the data we can gather in our testing. And with that, we can pass it over to Kelvin, the electrical sub.
Hello, everyone. My name is Kelvin Molitor, and I'm the electrical sub-team lead, as mentioned. This is my 4th year on the team, as well as my 4th year in school for a computer engineering degree. And I will talk a little bit what we do. It's mainly centered around power, data, and controls. Next slide. So yeah, one of our primary purposes is power distribution. Kind of by definition, all electrical components need electrical power in some way. And to do that, all of our power runs through what we call the power distribution module, as shown on the top right. This is kind of like a fuse box in the sense that it monitors for overcurrent protection. But in doing so, it can also log the current that goes through each channel, and we can quantitatively figure out how much power each of our components use to properly manage our power budget. As shown in the middle right there, we have about 400 watts in our electric vehicle, over half of it being with cooling. And then the electric vehicle, it's about 350 watts. So quite a lot of power going through just one PCB. It's a high power board and a lot of fun to design. All of this power is sent through an aerospace grade harness. As you can see on the bottom right, that's an example of an Autosport connector with what's called DR25 insulation around it. So this is resistant to both oil, heat, and any other corrosives that happens and goes along the engine. And it gives us very, very reliable wiring throughout our vehicle. Next slide. As you may have heard other people talk about, data collection is extremely important to the team. In fact, the primary goal of every drive day is collecting data to learn more about our vehicle. There are over 200 data channels on each car, so that is a lot of data. We actually target 1.5 megabytes per second of data, which is pretty equivalent to an HD video, which is quite a lot of data. Each of these, all of these channels are sent over CAN, which is a very common communication protocol on vehicles. All of the modules send data to a central module on the car, which logs it to an SD card that we can extract and look into our fancy graphs that you can see here. Some great examples were already shown, but a couple of my favorites here. Drivers really like using the display in the top right to be able to kind of see what they're doing. Drivers can even compare their laps with picture-in-picture to a faster driver to try to determine how to become faster and improve their performance. In the middle right, we have an example of our shifting that's actually logging the speed of each individual gear with reference to the output of the transmission to kind of show how fast our shifts are and where we could gain some time. Another one of my favorites is shown on the bottom left, which was actually a scenario where we starved our engine of oil because we were going too fast. You can see in the bottom middle, that is our oiling system. It gets completely uncovered. So we were able to take that data and import it directly into simulation software to see kind of post-mortem what happened inside the engine and why it failed. And then of course, use that same data to try to make it better. Next slide. The final thing we really work on is control systems. There's a lot of dedicated control modules on the vehicle. Some examples would be the transmission control module and the engine control unit on the internal combustion vehicle, and the vehicle control unit on the electric vehicle. Examples of what those do, we have the kind of main control system for the transmission controller on the top right. It's in charge of, you'll hear more about from the ergonomics on TV, but using pneumatic air pressure to hit our shift lever at very precise times in very precise ways in order to maximize the power and speed of our shifts. And the engine control unit, we use what we call engine maps, working very closely with engine to develop perfect timings and amounts of both fuel and spark in our engine to get the most power we can from it. On the electric vehicle, it's a little bit different. It's all very kind of electric in nature, as you can imagine. It uses sensors coming from the driver pedal going into a module, which runs some safety checks on those, and then asks for a specific amount of torque from our electric motor in order to get the optimal amount of grip in order to get our car accelerating as fast as possible. Some other things we need to do, specifically on the EV, there are many safety and rule checks have to do with just having an electric vehicle and the danger of that system. Specifically, the battery management system ensures that the battery is acting in a reasonable way at all times, and we always know everything we need to be able to operate it safely. And then our brake system plausibility device, which ensures that the brake system is working in a reasonable manner, so it will shut down the car automatically if we lose braking. Next slide.
Hello, I'm Jacob. I'm on my third year on the team, and I'm in charge of the ergonomics and controls. Or for ergo for short, for most use. So we're primarily focused on the driver and all the controls they have of the car. So we want the driver to be comfortable in the car and confident, because a confident driver is also a fast driver. And as such, we are responsible for the braking system, the steering, the pedals, the seat, and the previously mentioned pneumatic shifting system on the car, which I will talk about more on the next slide. Perfect. So first off, seat and steering. We make our own seats every year. They're designed to be comfortable for the driver, to really cradle them in the car. And to place them very low in the car. A good seat is crucial to a fast car, especially with us being able to hit about 2 Gs of lateral acceleration. You really want to be secure in the car and not sloshing around back and forth. Along with that, we make our own steering wheel and steering system in-house. So the carbon fiber steering wheel that you see in the middle was designed and manufactured by students, and the reason we use carbon fiber is it's very lightweight, and our own designs allow us to make them very functional and specific to what we need and very comfortable. And then in the bottom left, you can see the insides of one of our steering racks. It's one of the few parts that we don't make ourselves, but it is something we're looking at manufacturing ourselves. With the capabilities we have in-house. And then, of course, the most crucial is the bottom right, which shows Goldie sitting in our EV at the state fair earlier, or last year, I guess, and just, comfortable in the car. Next slide, please. Perfect. Then here is the pedals, brakes, and shifting. So we also design our own pedals, just a gas and a brake pedal, to be very compact given the sort of size constraints of the cars in this competition, and the sort of rigors of motorsports that they have to endure, especially the brake pedal. Along with that, we design our own brake rotors seen in the bottom right of the picture. We really want a high performance braking system, and we've been able to achieve that in the past. With these brakes, we hit about 1.9 Gs of maximum braking, which is quite a lot, definitely a lot more than you'd see in your road car. They're also one of the hottest components on the car. This fall, we hit nearly 600 degrees Celsius of rotor temperature, which is rather toasty, but necessary for a good braking system. And then finally, the pneumatic shifting system pictured in the bottom left is our paintball tank that we use to store air pressure, and then an actuator and a solenoid. And then the picture to the right of that shows it on the car. We use that for very fast and reliable shifting, with the control scheme that Calvin and his people have figured out. We've been able to hit shifts in less than 1/10 of a second, which, that's like snapping your fingers very fast. And that time is actually at this point mostly limited by how fast the engine can change revs. So I think we're doing a pretty good job on that. And I believe that is all I have. And I'm now passing it off to high voltage.
Hi, our high voltage powertrain lead, Sam, cannot be here today. So I'm going to go over a little bit about what that system looks like. Next slide. So the high voltage powertrain team handles the high voltage system of the EV car. So that's around 350 volts. That's looking at our battery pack. So what this team is mainly focused on is mechanical and electrical integration. So working on how we're combining our batteries into a mechanical system that's safe to handle and also rule compliant. Like I said earlier, the electric vehicle competition has a lot bigger rule book than the IC competition just because of handling the system and making it safe. So our high voltage power team does a really great job at making sure that A, we meet all those rules, B, we have a safe system, and C, it's still a high performing vehicle. So what this team consists of is looking at the battery pack. That's one of our segments is shown on the right hand side. It's also looking at the driveline of the car. So that has to do with the inverter, the motor, the radiator, just systems like that. And then also the tractive system. So anything that high voltage will go through, high voltage powertrain works on. So next slide. Yeah. So they're working to design, test, and validate the motor mounting solution. So we actually had issues with that last year, so it was being redesigned. They also do the high voltage wiring, so that's that orange tractive system, motor control, and then also working on making the system safe and easy to handle so our drivers feel confident. Next slide. Here's one of the other systems that we do is the accumulator. So that's holding the battery pack that is shown on the bottom left, simulating loads on the mounting, and then fitting components that control the system in that accumulator. The battery segments are designed to protect the battery cells and slot into the accumulator for easy maintenance. Also working with the electrical team on battery management, pre-charge and discharge, and then other control systems. Next slide. And next, I'm going to pass it off to our business lead, Tanae.
Yeah. Hi, I'm Tanae. This is my second year on the team, and I'm the business lead. I'll go ahead, next slide. So the business sub team is kind of responsible for 3 main areas. The first of which is marketing. So we handle all of the social media platforms such as Facebook, Instagram, as well as other platforms like our LinkedIn and our team website. Our responsibility is to basically take pictures and promote or bring exposure for our team across these many sites, as well as for our sponsors, and give them a chance to be for other people to see what we do here. Then there's also our internal administration side of it, mostly the financials. So the business team handles all of the budgeting, the purchasing, all the stuff that goes on behind the scenes to make sure that the team is run smoothly. And then finally, our university and sponsor relations is our third part. And that's basically handling everything to do with sponsors as well as the university itself. So departments like CSE give us money and we maintain relations with them. Okay, next slide.
And so I'd like to give a quick thank you to our sponsors. As you can see, there's a lot of local and large companies that support us, like Horton, Milwaukee, Prototype Solutions Group, Napa, EvoCharge, EMJ, Stratasys, SKF, ANSYS, and a few others, and many others, especially the university. The university gives us a lot of space and funding and really helps us do what we do, and we're really appreciative of that. And so, yeah, we'd like to thank those sponsors. And then I'd have a quick interest form. So this will take you to a survey. So if you're interested in joining, subscribing to like our newsletter so you can get updates about the team. And additionally, there's a spot where if you think maybe you'd be interested in sponsoring the team or helping out in some way, you can click that and we will reach out to you to see if there's some way you can help us. And yeah, I guess some other sponsor perks is at the end of the year, we always have a sponsor drive day. So a lot of the sponsors get to come and test drive the car, and they always have a good time with that. So I think now it is time for the Q&A.
Yeah, thanks so much to everyone. Just a note, we will be sending an email out with the link to the recording of this video. And in that email, I'll include links to some of the social channels where I know the group is active, as well as their website and to this interest form. So if you're not able to scan a QR code, I'll make sure that email has the link to take you directly to this interest form. So if you haven't already and you have a question for the group, please put it in the Q&A, and Wyatt is going to ask as many of those questions as we're able to get to in the next 15 minutes or so. And then I'll just wrap up with some closing announcements at the end. So why don't everyone turn on your videos and we'll get you in gallery view so everyone can see all of our participants, and Wyatt, you can go ahead and start directing questions to folks.
Unmute myself. I guess I'll start with the first question. Chris Yancher is asking, how many points do you plan on scoring to earn 5th place and 10th place finishes this year in each event? So I guess this is for Sophia and Will.
I gotta pull up the number quick.
I can start then, Will, while you pull up your number. So yeah, we're a 2nd year EV team. And the electric vehicle side of competition is very, very difficult. I went to a conference this past fall hosted by Tesla in California, where they let us know that of the past 3 years, there's been 314 teams that have competed at competition. And of those 314 teams, only 14 have actually made track. So 14 of those teams have brought a working car to competition that has passed technical inspection, which is when judges will go over your system, make sure it's what you said you built, and that it's safe. So that number, this is a really new competition, especially looking at the IC things where you can just slap an engine on that. We're building our own battery pack. And we last year did not bring a working car to competition. We brought one that we wanted to go check out the competition, see if we could pass technical inspection, which we didn't, but this year we're going to. It's fine. So looking at last year's numbers, there was only 6 cars that were brought to competition that competed. So when I set out my goals as the chief engineer, I was looking at the competition numbers. And if we bring a working car to competition, I'm fairly confident that we're going to score in the top 10. I have numbers for each of the specific events, but I'm prioritizing having a working system and having working drive days prior to competition. So that's kind of where I set my top 10 finish goal at. And I know with the IC, it's a little bit different, having kind of a legacy car and a legacy design.
Yeah, and for the IC, for that 5th place finish, we're targeting 748 points overall. This was kind of based off of our performance in this most recent year. and comparing that to the performance of the 2019 vehicle where we scored 9th place. Based on how like the landscape of the competition has changed post-COVID and kind of where we ran into issues this most recent year, that was a goal that seemed very reasonable. Just starting with some low-hanging fruit of like problems we had with our previous vehicle, and how much performance we could gain with increased testing time and mechanical changes to make the vehicle more reliable as well.
And I'll answer a couple quick ones. So how many hours per week do students generally spend working on the projects for this? That's a very varied answer depending on the person and the year. There's definitely I would say a lot of officers are putting in 40 hours a week just on the team, especially during busy times, when it's crunch time for manufacturing. But generally, I would say most members probably put in around 10 to 20 hours a week through the whole year. And then where we build the cars, we pretty much build them all in the basement of the mechanical engineering building. There's a couple things like from our machining we do on the main floor of the mechanical engineering building, but that's for the most part where it's done. And then there's a question: have you explored generative design tools, and do you have any 3D printed parts on the vehicle? I don't think we have any major 3D printed parts, if anyone knows, but we
I
do.
can actually expand on that. We actually use 3D printed airfoil internals for our front wing and rear wing elements. We 3D prints out of chop strand carbon reinforced nylon filaments. Has a higher dense strength to weight ratio we found than traditional composite ribs or aluminum. So we do have some 3D printed parts.
We also 3D print our segments on our battery pack. So we're looking at the filament type that we use and making sure that it's got the right properties to help electrical isolation. So we do have some 3D printing on our vehicles. A lot of that is outsourced, not done at the U.
Was the first part of that question like generative too? Is it just like material added processes, or like the design is?
The question was just, do we use generative design? And then it just asked the second question, is 3D printing, are there any 3D printed parts for the car?
I mean, I guess we do use some generative design, as in like our wheel centers, for example, use like a bone growth model, just inputting load cases and some basic boundary conditions, and then outputting basically the optimal design for a wheel center. We've also been testing that same method on a new wheel center design that might be coming not this season but next season.
I guess our project managers aren't here, but the chiefs can talk about this. When does the team plan to have drivable EV and IC vehicles?
First drive day for the IC vehicle is April 1st. That's the current target.
And then for the EV, it's 2 weeks after that.
And then a couple more. So how much supervision do we get for this event? Honestly, not that much. We're pretty much, the university kind of just lets us go to our own devices. Obviously, we ask for help for things like if it's, maybe like a really tough material science question for something like the brakes, maybe we'll ask for help from a professor. And then where do we do the driving? The primary spots is the State Fair parking lot. So, if you've ever been in Minnesota State Fair, that's where the buses go. So that's mostly where we do driving. And there's a couple sponsors who allow us to drive in their parking lots when the State Fair lot isn't available. And we try to do in the fall and spring if we can get the car driving every day. Every weekend, not every day of the week. There's some questions for the EV. So is there more than one motor on the EV car, or is there regulations on the number of motors on the EV car? And then also, does the EV have traction control?
We currently only have one motor on the EV. Some teams do too. When that conference I went to last fall talked a lot about what makes a successful EV car. So they took that data of those 300 teams and analyzed how many motors they had, what kind of inverter. We use a Cascadia motion inverter, and how many motors, what kind of motor, what kind of inverter, and trying to analyze like what teams are doing that are very successful. So it is possible to do 2 motors. I don't feel like we're definitely not at that space yet on the EV side of things. That's something that we're going to be looking at in the future once we get to bring a driving car to competition.
And yeah, as far as traction control goes, we do plan on running traction control. It's relatively simple, kind of very similar to a combustion scheme where you just reduce torque under conditions where the wheels aren't giving you what you want, as well as multiple motors. Kind of the dream that some teams run is what are called in-hub motors. So they'll put 4 individual motors on each of the wheels and send specific power to each one based on the current conditions and the current driver inputs.
Here's a question for Enders. What is the main reason to use a pneumatically actuated stick shifting system?
So for a long time we ran just like a hand lever with a clutch thing, basically just take it off the motorcycle. The big disadvantage of that is that it's relatively slow and requires the driver to take their hand off the wheel, which is bad for peak performance and also just safety of the car. You have less control with one hand off the wheel. The reason we decided to switch to a pneumatic system is because it's relatively light. The big weight is the paintball tank we run. The other option that we've looked at is an electric system, but the issue with that is that it requires a lot of power. I think it would be more power draw than what we have currently for the whole car, like just to hold the clutch open. And the one big downside to the pneumatic system is that it has a limited runtime just based on the size of the tank. But for this competition, we know exactly what our maximum runtime has to be. It's that 22-kilometer endurance race. So we can size our tank based off of that. And sort of with the size of pneumatic actuators that we need to use for this, we should be well in the clear with even some of the smallest paintball tanks you can get commercially. So that's why we run it.
And then there's a quick question. Will there be a car unveil event this year? We hope so. That if we reach the goals that we expect to, as far as building timelines, we do plan to have one. And then do we have a designated test plan for figuring out optimal settings for each dynamic event?
Yeah, so we do test the specific events. We didn't run any event specific setups just due to this past season, just due to like when we got the car done and how much tuning time we actually had. Along with how much time we actually had at comp between events where we could change setups. The goal is that we have specific setups for each dynamic event, Excel, skid pad, endurance, autocross. Endurance and autocross test setups will be vaguely similar unless for some reason the cooling requirements are different, and we have to change the aero at all to account for it. But for sure, skid pad, Excel, and the 2 actual track-based events will have separate setups.
So I think a couple people asked how many events there are per year. So each car has its own event, and they're both at Michigan International Speedway this year. There used to be a couple events that we could go to, and we've gone to 2 before, but nowadays there's only the one per vehicle. And so the IC one is in May, and then the EV one is in June. And then anyone can answer this question. Has the experience on this team help you with communicating to hiring managers, and what were your successes, and Do you think these experiences will present you as an effective employee at the company?
I guess I can start with that. My experience with the interviews is I basically only talk about the team. The second they look at my resume and see the relevant experience, they kind of throw classes out the window and just want to talk about it, as well as it being just a really fun thing to talk about overall. Usually engineers are very interested in the kind of engineering that goes into it. So I feel very, very prepared by this team.
Yeah, I'd like to add on to that. From what Calvin said, as soon as they see relevant experience, that's so much more useful to a hiring manager, I found, than relevant class experience, as well as just passion for the team. This team really is conducive. We're really passionate about what we do here. And the hiring managers, from my experience in interviews, love to see that. They love to see that we get passionate about what we do and are excited to talk about it, including, what went well, what didn't go well, and how we learned from it. That's the biggest thing, what we learned from our failures and our successes. And the hiring managers love to see that. And it's been very successful for myself and as well as the rest of us here.
Yeah, when you have like this sort of stuff, even if you just have it on your resume, like, and you have projects and you know what you're talking about, if they ask you questions about the projects, like interviewers, like any technical interviewer is just going to hyper fixate on that. Like it'll even overshadow like previous technical experience at like other jobs even. They really just want to hear about the project based aspect. And that if you really know your stuff, and you're willing to like go really in depth on what you did in the project, that's what makes all the difference.
I think the other part of that too is that a lot of our sponsors send us applications that they want our team to apply for. They know the type of engineers that are on the team and the type of experience that they're going to get. And we have good long relationships of interns at the company succeeding. And so they really do like to hire from Gopher Motorsports.
This is a question for Alex, I think. How do you procure the carbon fiber layups? And maybe you can elaborate on the process of that a little bit more too.
Yeah, sure. So on the aerodynamics side of things, we do wet layups mostly. There's two different kinds of carbon fiber manufacturing, your wet layups as well as your pre-pregs. That's probably more geared towards pre-pregs, but essentially a pre-preg carbon fiber is carbon weave with cross-linked resin in there, which we then cure in an autoclave at a sponsor at 3M. We do this for our monocoque, our external layers, our layers of carbon on either side of a sandwich structure. Pretty much put the carbon part in the tool under pressure and vacuum. This sets off the chemical reaction inside the resin, causing the matrix to solidify, giving us a stiff carbon fiber part.
There's a question about how many people are on the team. I guess, yeah, I never said that specifically. I would say there's around 40 people on the team. We haven't done a survey about like the official number, as there's some people who can't put as much time in, but I would say there is at least 40 people putting 10 hours a week in on the team, if not maybe close to 50. And obviously there's fluctuation with classes and things. Some people just they don't have 10 hours a week to give to the team, but yeah, I'd say that's about it. There's also a couple of questions about how we do knowledge transfer and kind of keep things going from year to year. So all the officers are elected at the end of every year, and so every position's up, and typically it's usually juniors or seniors and the occasional sophomore that is chosen for those positions. And then kind of knowledge transfer, that was definitely something we struggled with during COVID. I mean, when we learn by building the cars and asking for help and figuring out. So it's a big learn by doing thing. And when we weren't building a car, that was difficult. And so we definitely had some hiccups last year when we were building the first car. But now it's really just making sure that that the freshmen that join are getting designs and really learning everything about the process. What's that? Oh. Does anyone want to talk about the driver development process? I suppose Enders, you're in it, so.
Yeah, I'll talk about the driver real quick. So one of the big rules for drivers in this competition is that they have to, in fact, be active team members. You can't hire out like your local karting champion or whatever. So with that, the way we set it up is that I don't know, a couple weeks into the fall semester, we'll generally start the driver tryouts process, where we'll just have everybody who's interested sign up. And then through various rounds of sim racing. So we have a setup in our shop that allows everybody to race cars on a computer, which is fantastic training. Through consecutive rounds of that, we will sort of figure out who is fastest, who is most likely to be able to do well in the car. And then once we get it down to about 5 or so people, and usually in the spring semester, once the new cars are up and running, we'll have these sort of final tryouts where people get the actual chance to drive in the car, for the aim of also driving them at competition later that semester. And then those drivers will continue driving for the rest of, or as long as they want to. Generally, it's none of the drivers, as far as I know, quit partway through their time on the team. So these cars are very fun to drive.
And there's also some questions about the inverter we use and the success we've had with that, specifically if it's a Cascadia inverter.
Yeah, we have a Cascadia motion inverter. We haven't really tested it. It's been really difficult last year without having a working system. And then just we kind of battled our Orion BMS for a long time. That was what was giving us the most challenges last year, which prevented us from driving. And then this year, yeah, we're still using that same Cascadia motion inverter. We haven't run into any issues yet, but I mean, we haven't really had a lot of experience with it. We are trying to finish things on the EV side as early as possible. A lot of the systems that we're using are reused from last year, because we know we're going to run into a lot of issues as a first year driving car. And so we are trying to be proactive about that.
And we have time for one final question. And this, I'll open this one up to everyone here. And what is your favorite part about being on the team? I would say for me, it's just getting hands-on design work and seeing the cars run. It's a lot more interesting and fulfilling, I'd say, than a lot of classwork. So I really enjoy that. Kelvin, you can go next.
Yeah, I would say my favorite part is twofold. The first one is easily the people I work with. It's just so much fun to be on a team. Everyone is super passionate, super happy about what they're doing. It just leads to a wonderful development environment of everyone working hard towards the goal. And then my second favorite thing is, I would say, when things go wrong. I really like improvising solutions on the fly and working to kind of make something work when there's no other options, which unfortunately has to happen quite frequently. It just, testing days keep a day alive.
I'd say for me, my favorite part about being on the team is seeing the people I work with grow as engineers and as people. I noticed it especially as I've transitioned to a leadership role from a design role, was last few years, seeing new members and returning members develop their understanding specifically of race car aerodynamics. That's been fantastic to see, and guiding them on that process, and learning with them, learning with them as they're learning. I'm also learning about just essentially what we're passionate about. That's what I find to be the most fun, as well as, like Calvin said, getting stuck into a design, really focusing on a design and seeing that design go from scratch on a whiteboard to actually getting it modeled in CAD to manufacturing it, putting it on the car and testing it and seeing that the design you made did or didn't work. You learn so much from that, and the design process is incredibly fun, in my opinion.
For me, my favorite thing about being on the team is getting to two things. First, being able to apply what you learn in classes. I feel like at the U, we're very theoretical based, and all of a sudden when we get to be on this team and you're using CAD and then you machine your own part, I think that's just the coolest thing ever. And I'm really glad I had that experience. And then also the people I work with, I feel like we have a really great camaraderie on the team, and we do really great about answering questions, mentoring like the freshmen, the sophomores, maybe some of the juniors, and even like the technical and the non-technical aspects, like preparing people for job interviews. And then we all just have a really great passion about getting these cars driving, and having a successful car competition. I think that's really cool to be united on a common goal.
I suppose for me, it's a little bit of a different experience because I'm not actually an engineer. So for me, my kind of favorite part about this team is that as someone who's like really interested in motorsports and the stuff behind cars, it's a place where you can actually come and see what it takes to build a race car as well as be involved. So, you know, I may not have all the necessary skills and know how to build an engine, but I can sit and watch people and know people that do know how to do that and be able to kind of experience all of that from more of an internal perspective as well.
For me, I would say, I think my favorite part is just kind of how it changed my perception and the way I think. Both like looking back at what we've done as a team and also what I've done as an individual. It really kind of puts me in the mindset of like, wow, like looking back at what we've done, like I feel like I could do like the next step now, like things that I never would have thought, like, oh, how do you design like an entire car? And then looking back, having like done it now, like in my 4th year on the team, like really like what a group of people can accomplish if they're just really passionate about it is kind of amazing. Just a bunch of students, like I find myself stopping and thinking like, wow, this is really cool. I'm doing this as like a junior in college, or from some of the stuff I was doing last year. Like no one else gets to really do this. So just the experiences we get to do by putting everything we have into a project, very cool to be a part of.
I guess I'll go next. I'd have to agree with what I think Calvin and Sophia said, that it's just a fantastic group of people to be with. I would not be spending this much time if I didn't like the people I was with. And along with that, sort of the practical engineering aspect of it, not just sitting in a classroom, actually getting to put that to use is a really fun time, and also just learning about all of the intricacies and various details about designing and making race cars. And obviously you get a race car out of it at the end, which I think is incredibly cool to have. So
Wonderful. I think we got to everyone, and I see we're at 1 o'clock. So just a quick wrap up announcement from me. First of all, please join me in giving a huge thank you to all the students who made time to share their amazing work with us today. Every time I hear the students talk about what they do in their student groups, I'm just amazed at how much they can accomplish while still being full-time students. So thank you all for sharing the many aspects of the work that go into creating that final product. And as a reminder, we'll be sharing a link to this recording. Please feel free to share it with anyone you think would enjoy it. And it will also include links to the Gopher Motorsports webpage and some other resources if you'd like to learn more about them. And just a quick shout out, if you're looking for another event to attend sometime soon, we have Bell Museum Space Fest coming up next weekend, Friday, February 3rd through Sunday, February 5th. There's 3 days of lots of different activities. A NASA astronaut will speak. They have a brand new planetarium show about Mars. So if you want to check it out, it's at z.umn.edu/spacefest2023. And if you're looking for more events to attend, you can always go to our college event website. It's got lots and lots of events happening throughout the year. That's at csc.umn.edu/event. And if you ever have questions for me, you can always reach me at cscalumni@umn.edu. So with that, I want to thank everyone so much for making time to attend the webinar today. And once again, thank all of our student presenters. Thank you so much and have a wonderful rest of your day. Take care.